recorded on this computer here. All right, so there we go. So a couple of first things, 2, 3 weeks ago when we were in class, we were discussing, or a little bit, or at least I was mentioning, that British Columbia was having some pretty massive floods. And they went down a little bit, and then they've got hit again with another basically 8,000 kilometer long uh, um, atmospheric river streaming in to northern British Columbia and southern Washington state, and have just been getting torrential rains again. And so these are from the last couple of days of flash floods happening and landslides that have then been combined with floods and wiping out parts of communities and roads and highways. In Abbotsford, which is in British Columbia, they have a couple of really interesting river flows, and they actually drained a lake back 150 years ago or so to build the town there. And now the river is trying to reclaim its former lakeness. And so they've actually closed a couple of the interstate highways in this town going through there and built emergency dams going across it to prevent the water from rushing into the city and washing into that lake again. So that's how bad it is. I mean, imagine closing Highway 99 down or something like that, and then people putting, temporary dams up by the bridges so that it prevents flooding in a nearby community. And that's what's happening there. So it's just really intense. And then when we talk about, the crazy flooding that's going on up there, if you take a look at this is a couple days old now, but kind of valid all the way through next week at least. And a lot of helicopter outside, sorry. You can see this is the total precipitation percent of normal. And we're down in the, close to 0 to 1% category down here, less than 5%. So it's going to be a dry week, and it, maybe mid-December, there's hints of forecast changes of maybe getting some rain and things, but it's not looking really great. So not only is it going to be dry, but here's what we see up here. It's called the temperature anomalies. And so we're going to see what these different pressures mean today. But 850 hectopascals is basically, a few 100 feet or so above the surface of the earth, not too high off the surface of the earth. And it's basically showing, what are these temperature anomalies? How much higher or lower are they going to be than average? And if you look at California, look at this, we're in this really big swath right here where it could be about 9 degrees Celsius, 9 degrees Celsius above normal, if these kind of play out to fruition here. So, it's going to be warm the next couple of days through the next part of these weeks. So warm, dry, and some other things to note is taking a look at the root zone, the soil moisture. So even though we had that rain in October, right, and we had a few little, little bits of rain in November, like just less than a quarter inch or so at the beginning of November, for the most part, our soils down by the root zone are already really dry. And we can measure this as much as easily every single day using what we call this GRACE satellite. I can't remember the whole acronym, but it's like gravitational something, something, something. That's what it stands for. But basically, there's these 2 satellites that are in orbit around the Earth, and it can literally measure the gravitational pull of different objects like mountains and things like that. And when there's more water in the ground, water has mass and exerts more gravitational pull. The satellites can measure that. And when the mass is gone, the satellites can measure that too. So what they're measuring right here is there's gravitational anomalies because there's not very much water in the root zone right now, which is a pretty amazing thing and a pretty cool way to monitor what's going on around us. Obviously not the case in like Mississippi, Louisiana, and places like that. And even in Northern California, right? They had hanging on to some of that water from those rains in October. All right, so that's kind of the geo news to think about. And then what we're going to be looking at today, this is not the first thing we're doing. I just put it over here because that's where it fits. But basically, we're going to be taking a look and making kind of an idealized global wind pattern for our sketch notes here. how does the wind move around the earth, and how does that tie into the atmosphere? We'll do some quick sketches of how to identify high and low pressure systems, identifying how air rises and falls and cools and heats up as it changes, as it goes up and down the atmosphere. So that's what we're going to be taking a look at. All right. And all of these will be pretty self-evident once we get there. And it looks like a lot, but it's really not that much, I promise. All right. And this one we're going to draw together. So it should be pretty easy, I think, for everybody. So just to recap, 2 weeks ago, if you remember, I took you on a little journey on this Google Earth tour, and you guys were filling out things that you happen to notice and wonder and compare different sites in California in terms using their climate graph. So basically comparing their rainfall, comparing their high temperatures and low temperatures and things like that. And, there were some really interesting patterns that started to emerge, like down here in, very Southern California. If you went to El Centro, its climate graph was showing, man, super hot summers, right? 105 is the average in July and August, super hot summers. And it cools down to, maybe the mid 70s at night, low 80s, somewhere in that neighborhood. That's kind of the swing. But if you go not too many miles away, just to the west near San Diego, look at that, right? You have those lower temperature swings. The high temperatures are barely what the low temperatures are in El Centro. And just kind of interesting. And notice the temperature spread is not as great between those two. So that's what I was having you guys take a look at. And now we're going to start today trying to figure out why are places on the coast, how come their temperature ranges are not as great as places that are further inland. So you can see like these temperature ranges are much higher, hotter in the summers, much cooler in the winters. And places like San Francisco and Big Sur, they just kind of stay, they have a little bit of a warm season, but it's a pretty flat differential in range of temperatures there. That's kind of interesting, I think. All righty. So that's what we're going to take a look at and try to tackle and try to figure out today. Oh, let's see here. All right, so here's a couple of big things that you need to know. So what are those things then that are going to affect the temperature in different areas, and especially in different areas of California? California is such a great example to use, right? Because we have so many varied geographic regions. We have what we call microclimates. So if you've ever been to like Santa Cruz or Monterey or something like that, you could literally be in a canyon near the coast and, it's foggy and, 55 degrees, and you walk literally a mile away over a canyon or up a hill or something, and it's maybe 75 or 80 degrees, just a mile away, depending on the way the canyon is facing and things like that. So California is a great place to talk about these temperature controls. And, hopefully by the end of this, you'll be able to take a look at weather forecasts and things like that and kind of get a better understanding of what's controlling the climate in the area and what's controlling the temperature that you see. And so, maybe when you go to Christmas vacation or winter break, you'll be able to, use your skills to impress your friends and family about how you can kind of tell them what to expect for different weather phenomenon in different areas. I don't know, it's a nerdy thing to do, but it makes you feel good, or it makes me feel good anyways. All right, so there's 4 factors that control these latitudes, or other than latitude, I should say, that influence temperature. And I want to double check and just reiterate that last week we talked about the latitude on Earth, whether you're close to the equator or closer to the North or South Pole, that has the biggest effect on a place's temperature, right? The amount of solar radiation that comes in, if you're near the equator, you're getting very much more sunlight that's more overhead and more direct, and it's going to impart more energy per unit area down there, versus if you go to the poles, where the sunlight is much more coming in at a lower angle, it spreads out more, the energy spreads out more, and you don't get as hot up there. So these are the 4 other things that control temperatures other than latitude. All right, so it's heating of land versus water, altitude, geographic position, and cloud cover. So let me show you some examples kind of each of these things of what I mean. All right, so we'll be talking about heating of land versus water. The oceans, and we're using here kind of an example of Vancouver and Winnipeg in Canada. So basically they're at the same latitude. So right, we're making sure that our comparison in terms of latitude, in terms of solar energy, is about the same for each place. But what you notice here is Winnipeg, woo, look at that. Winnipeg has a much has a much larger temperature range between summers and winters, right? I mean, look at that. So here's Fahrenheit on the right hand side, if you're more familiar with Fahrenheit, but we're talking, down near freezing for most, or not freezing, but 32 degrees is freezing, right, in Fahrenheit. So we're talking well below freezing for several months of the year in Winnipeg. And then in summertime, it maybe gets up to 70 or something like that. Whereas you compare Vancouver, same latitude, but Vancouver, it never gets below freezing, which is 0 degrees Celsius, right? It just hardly ever gets below freezing. And that has to do with being close to large bodies of water. And the one thing to know is that land actually heats up and it cools down more rapidly than oceans do. So it takes a lot more energy to heat up water and make it change its temperature. You probably know this if you make coffee or boil pots of water or stuff like that to make soup or anything, right? You have to put the pot on the stove full of water, and it takes several minutes for that water to heat up with just all that flame and energy going underneath it. If you just put an empty pot on there, just completely metal, and you put that burner on, right, that pan's going to get hot within a matter of seconds and cause some problems. And so the land is very similar. Its properties, its molecular properties allow it to heat up much more quickly, but it also gives off that energy much more quickly. Whereas oceans takes a lot to warm it up, but once it's warm, or once it's at a certain temperature, it also has to lose a ton of energy to cool down. And so what's kind of interesting is when they live near the water here, when folks live near the water, the ocean during the summertime, the ocean in the Pacific here is cooler. So it kind of imparts its cooling mechanism. If the ocean is only 58 degrees and the air temperature is like 80, that ocean is going to act as an air conditioner and chill off that bottom layer of air and kind of keep things pretty moderate and mild down there. And the same thing happens in the winter. If it's trying to be super cold outside, that cold air coming has to go across what would be relatively warmer water. It stays, assuming it stays like in the 50 degrees or so, it doesn't cool down. Cold air coming from like Canada or places like that, or northern Canada, would have to go across this body of water. And because it's relatively colder than the water would heat it up. All right. So that's kind of one of the big things there. So, and oh, by the way, I just should mention too, the elevation differences between Winnipeg and Vancouver are not that different as well. And we'll see in a few minutes that elevation does play a huge role, like right now with altitude. So, proximity to oceans is a big thing. All right, that's one thing. So that's why places like San Francisco, Big Sur, San Diego, that's why their temperatures are so moderate. That ocean water is a huge moderating factor. So it cools things down in the summer, and it allows and it gives off heat in the wintertime and warms the air above it, which is pretty cool. Yeah, it cools and neat, not that it cools it off at that particular time. So anyways, altitude is the second major temperature control. And so this picture I took at Sonora Pass, it's about 10,000 feet in elevation. That's my summer getaway. And I'm assuming some of you guys have had the opportunity at some point in your life to hopefully get up to the mountains and experience, that indeed in the summertime, if you go up to places like Pinecrest or things like that, it's generally much cooler than what it would be in Turlock. So, it's like 100 degrees in Turlock, it's probably only 80 degrees or so up at Pinecrest. And there's a reason for that. And the reason for that is, right, the sun, when it hits the ground, that sun's radiation is absorbed by the ground, and then that radiation is radiated back out as infrared radiation. So it comes in as short wavelength light, and then it gets absorbed, causes the ground to wiggle, causes it to get heated up, which causes it to then radiate out infrared radiation. And so as that radiation kind of leaves from the ground and goes up, it spreads out, it loses, or it's basically starts imparting some of its energies to the other parts of the atmosphere. So as it rises, it actually cools off. And that's why when you go higher up in the mountains, the air is cooler because you're higher up from kind of the average baseline of the elevation that surrounds you, and things are cooler up higher. And so there's kind of a rule of thumb. For about every 1,000 meters you go up from sea level, basically the atmosphere changes about 10 degrees Celsius for every 1,000 meters, or 1 degree Celsius for every 100 meters you go up. And if you want to put this into feet and Fahrenheit, basically for every 1,000 feet you go up in elevation, the rule of thumb is it generally is cooler by about 3 degrees Fahrenheit. So like Sonora Pass, 10,000 feet in elevation, it's going to be 30 degrees cooler in the summer times than what it is down in Turlock. So that's why I can't get enough of hiking in the mountains in the summer. Not only is it cooler, it's just a good place to be. All right. So that's one cool thing. And here's a little case study. So Quito and Guayaquil down in Ecuador, really interesting places. Notice they're near the equator, so their climate graphs are pretty steady year round, right? Because they're near the equator. The sun angle doesn't change that much during any given part of the year. But what's kind of interesting here, Guayaquil is down near at sea level, and Quito is a big city at 9,300 feet in elevation. So can you imagine like living at the top of the Sierras or something like that, and just, you know, it's light, the atmosphere is lighter, there's not as many molecules up there, it's harder to breathe. And, you know, that's just city life up there, 9,300 feet. And when you walk outside, even though they're near the equator in Quito, you know, maybe it gets up to 60 degrees, but pretty much the average temperature year round is like 58 degrees, 58 degrees, 58 degrees, pretty much doggone year round. And same thing with Guayaquil. It's pretty much, you know, within the high 70s or low 80s almost all year round. But these folks are down near sea level. These folks are higher up in elevation. And so that's why the temperature changes are definitely noticeable there. All right. There's another one called geographic position. And so this kind of has to do with being near the oceans as well. But there's a little bit more to it than just being near the ocean. This one has to do with being near the ocean and the direction of the wind. So take a look. New York City and Eureka are about at the same latitudes. They also are both near oceans. That's a big thing. The ocean that runs through New York City here, this Gulf Stream current, it's about 70 degrees or so, 75 degrees, which is why like it's so weird for me to see people on the East Coast going to the beaches and swimming in the oceans and stuff like that. You don't see that as much in especially Northern California because we have colder currents up until about Santa Barbara or so. We have colder currents that makes the water like 50 degrees, 58 degrees, and nobody wants to swim in that. Not me anyway, it's too cold. All right, but check this out. Eureka has those much more moderate temperatures, just like we were talking about earlier from that sea influence. And places like New York City, though, it's got really quite a big swing. It gets below freezing in a couple months out of the year, and it has much higher temperatures in the summertime than Eureka. So the reason for this is the wind direction. Generally, the wind patterns blow in the United States, at least in this latitude, from west to east, right? They blow from west to east this way. So Eureka is basically having wind blown onto it from the ocean, and New York City is basically having wind blown on it from what's coming off the continent here. So it's coming off the continent. It's usually drier. It's usually a little bit warmer in the summer times. In the winter times, it's generally cooler and drier. And so, you know, any of that cooling effect from the ocean is kind of blown out to sea and not blown inland where New York City is. So that's kind of how geographic position can influence it. There's also a couple of other ways that geographic position can influence temperature. So Seattle, Spokane, not too far away, and you can think of any California cities, like you can think of Turlock versus or Reno or something like that. A very similar thing would happen. But sometimes mountains act as barriers and they prevent kind of that moisture and that moderating effect from the sea from reaching over the mountains and getting over to the other side. And so we can take a look and see how Seattle is much more are much less pronounced than Spokane here. And the main reason for that is it has to go over a big mountain range. And so that's Spokane down in the bottom left. So I'll show you why this happens in just a few minutes, but just know that if mountains are in the way and the wind direction comes from one side to the other, the places that are on the windy side of the mountain, the windward side of the mountain, are going to be much more moderate and probably rainier than the places on what we call the leeward side of the mountain, or the other side of the mountains where the wind is blowing over and into. All right. And then, so those are the first three. The last one is cloud cover, and albedo really causes big temperature controls. So think about places down like in the tropical rainforests around the equator, jungles in Africa, jungles in South America, like Brazil, places like that, right? They get lots of rain, they get lots of evaporation, and that cloud cover can act as extra albedo, reflecting sunlight back up into the sky, but it can also, can trap in heat and radiation and prevent it from leaving. So cloud cover and albedo also play a sizable role on basically diurnal temperature ranges. Diurnal means the daily temperatures. So do you remember last week or a week and a half ago when it was really foggy there for that period of time? Fog is just a cloud that's on the ground, low elevation cloud. But what's pretty interesting is, if you remember, right, the low temperatures would only get down into maybe the high 40s or low 50s at night. And then in the daytime, if we were lucky, it warmed up to like 50, 53, 54. So there's only like a 5 or 6 degree temperature change between night and day. And now fog is cleared out, and now we're getting temperatures into the low 40s in the early morning, and in the afternoon it's darn near 70 degrees, right? We have a 30-degree temperature change, and that's because there's no clouds. There's nothing there to moderate the temperature. So during cloudy days, it doesn't let as much radiation, clouds don't let as much radiation into the ground, and things don't get heated up as quickly, all right? But at nighttime, those clouds kind of act like a blanket, and they trap radiation from leaving, and it keeps you warmer. So by having less warm days and more warm nights, it keeps that temperature swing much more moderate. All right, it keeps it much more moderate. And this is what we would call a diurnal temperature graph here. So it's a 24-hour temperature swing. You can see on an overcast day, the lows don't get very low compared to a clear day, and the highs don't get very high compared to a clear day. And this is, if you've ever been to a desert like Death Valley, or anywhere in southeastern California, places like that. I mean, I've been to Death Valley where it's 85, 90 degrees in the day, it's like February or so. And then at night it gets to like 25 degrees. Like, oh man, it just gets so stinking cold. And then that sun comes up in the morning, and I feel like a lizard or a cat. You just want to go find that sunbeam and get warmed up here. But that's how clouds affect that. And then also, I just wanted to show you this too. You can see, so here's the coastal currents off the coast of California here, and what you're seeing, these different colors, and I don't necessarily agree with the color schemes of this, but whatever. We're talking about very cool temperatures of ocean waters and things just off the surface, just off the currents coming off of the current of California here. And you can see how it's nice and cool, but you get inland into the valley, it gets really doggone hot. You go up high into the Sierras, and the altitude causes it to cool down. And you notice anywhere that the continent that is near the ocean here is much cooler in the yellows than inland in the valleys here, which is just kind of cool and interesting to see. And look at the delta, right? This is where the delta breeze will come through and cause some cooling if they're near the bodies of water there. So, all righty. Now, here's the fun stuff. So what I'm going to show you now is we're going to talk about convection really quickly, because convection is kind of one of the main driving forces of our atmospheric dynamics here. So it all starts with an uneven heating of the Earth near the equator or near the poles, right? The equator is super warm. The poles are generally much, much, much cooler than the equator. And so when you get these temperature imbalances, it allows things that are hot to try to go to areas that are cold, right? And things that are cold kind of get pushed and migrate down to areas that are warm. So I want to show you kind of convection in a little bucket here. And what you're seeing is just a shoebox, plastic shoebox. It's sitting on top of 4 cups. And then underneath it, here is a cup of cold ice water underneath it. So it's not actually in the tub, it's just underneath it, kind of cooling it off like an ice pack. Another bottle of cool water, and you notice I have the blue food coloring there. And then guess what's underneath the red one? It's a cup of hot water. So like, you know, hot chocolate temperature, coffee temperature water underneath here. And so it's going to be radiating heat on top of this food coloring. And food coloring is pretty cool because it's dense. And if you put it down at the bottom just right, it'll stay stuck on the bottom until you put something underneath it. And here's what it looks like. So you can see after that first little bit here, the heat keeps rising and rising, and then it hits the top of the surface and it has no place else to go except out, right? And so I want you to think about, this is very similar to what happens in our troposphere, where all the weather on Earth happens. And you can think of this line as kind of like the tropopause that separates us between the troposphere and the stratosphere up above. But this warming stuff, it starts rising because it's warmer. And as it's warmer, it expands, it becomes less dense. And that's why it goes up. Very similar to a hot air balloon, right? Hot air balloons go up because the air is warm, it expands, it becomes less dense than the surrounding air, and it provides this buoyant force. So that's what we're seeing here. And in this case, it's just water with red food coloring to trace it. So it gets up to there, and then it has to make room for the other stuff that's still rising underneath it. So as this stuff rises up, it pushes out everything else to the sides here. And so after it gets pushed off to the sides, it gets away from that heat source. And as it gets away from that heat source, it starts cooling down. And as it starts cooling down, it becomes a little more dense, which, as you can see, it starts sinking, right? So it becomes a little bit more dense and starts sinking down. And not only does it start sinking down, but you can see the blue stuff down here is making its way to the middle of the red. And that's because as the hot stuff rises, you can't leave a vacuum or a void there. It has to pull in molecules of water or air from other places that are surrounding it. So as this stuff rises up, it literally creates what we call like a low pressure and brings stuff in from the other places. So what was cold brings it over the warm. And when it gets warm, well, look at that. It heats up, becomes less dense, and starts going up as well. And you can start seeing then it makes what we call this convection cycle as it starts spinning around. So it heats up, cools off, goes down, heats up, cools off, goes down. And you get this kind of bigger picture until the blue is really dark and it just all blends in. And I was taking temperatures there to show temperature differences in that particular one, but it's not a big deal for us to think about that. So we are going to take what we just saw here and we are going to try to diagram. And let me make sure my thing works here. Oops, let me see. Bug on it. Let me make sure my pen thing works. Holy moly. Hold on. Well, it was working. Give me one quick second here. What the heck? Got some serious flickering issues. Hey, what the heck? Come on. Sorry, you can hear the boopity boopity. That's this trying to work. So let me see if I can get it open here. Give me a quick second. I don't know why it's having some issues, but I think we'll try to work through it. All right, so let me share my other screen in just a second here. I think maybe my cat sat on it. That might be the issue here. Stinking cats. I love them, but give me one quick sec. Let me get the pictures here for you. There we go. All right. So I got to erase a couple little things here really quick. There we go. And then we'll be good to go. So this is something that you guys are going to be wanting to put on your sketch notes. Yeah, for sure. And we'll be talking about it and adding to it and showing you some really cool things I have a little demonstration to show you, I think, before we leave. That should be pretty awesome too. All right, so let me share the right screen. That's what I need to do. All right, and I hope it's just my screen that's flickering and not everybody else's. Oops, give me a quick sec. Man, it's stinking. There we go. The Zoom mouse button is a little funky here. All right, so here's what we're going to do. Here's our Earth, and what I want to do is I want to kind of mimic this, what we just saw with the convection happening here. And so I'm going to draw at the equator here. At the equator, I'm going to draw a couple of arrows that goes up like this. All right, and so I'm going to imagine, and just to show you, to get you an idea of what I'm thinking about here, I'm going to put a little person right here, because if you're standing at the equator, this is kind of how you'd feel, right? I mean, you're kind of standing sideways. So if you're doing that, the air is going to be rising straight up around you. There's lots of energy, lots of things going up. So that's the first thing to think about, right? Is we're going to have this warmer air rising, and that's kind of the first concept. Hopefully, I can. Let me get this. There we go. Oops, come on, red. I want red. Close enough. All right. So I'm going to say warm air rising. So that's what those red arrows represent. All right. That's the first big part. Then once that air got up a little ways, right, what we started noticing was it started kind of going out to the sides. So it started kind of going out to the sides like this. And that's what exactly happens in our atmosphere as well. We get this kind of cool pattern that emerges. And this is kind of a generic, idealized version. It's not exactly what we see every single day, but it's kind of a good model to start with, right? So here's the thing, right? As it gets up higher, notice I'm turning. I turned my color here to bluish, somewhere like that. And what I'm showing here is as that air starts spreading out and getting away from the warmer areas, and as it rises, it kind of cools out. And as it falls back down to the Earth here, because it's colder air, we're going to see some funny things happen with this a little bit later on. But basically, this cold air kind of falls back down to the ground. And that warmer air that was already on the ground, right? Just like we saw in our video clip here, once it hits the ground like this, that ground air is going to start working its way back to where that area of low pressure is. It's kind of being brought in right here, and it creates this nice convection cell, these convection currents that happen here. And now this is going on basically all around the equator, so everywhere around here, but I'm doing the side view because it's a little bit easier to draw and see and visualize this. So if you can imagine like a tube of air wrapped around the entire globe, this is what would be going around it right there. All right, so that's kind of the first part. That's the first part. The second part to all this, though, is remember we talked about the poles being pretty doggone cold. So check this out. So at the poles, right, we have sinking air pretty much to begin with down here, just because it's stinking cold. And so that cold air kind of gets pushed down, and it forces its way kind of down. And as it forces its way down and goes across the land, it generally warms up just a little bit. All right. So it generally warms up just a smidge. And as it warms up, well, guess what? It starts rising again. And as it rises, it makes its own little convections. Oops, let me get my blue. Makes its own little kind of convection cell up here. So the exact same thing happens. Let me get, I'll just put the red in here in just a minute, like this. All right. And this would also happen at the South Pole, definitely would also happen at the South Pole, very similarly to this, depending on the time of year. Okay. So we get that happening. And not only do we have some of the warmer air rising here, but it also happens right next to it, like this. So we're going to have this rising air kind of like this. And as it goes like that, it starts cooling down. Woo. Starts cooling down and sinking. So we have an area of sinking air here, And as it pushes down, it forces some of that air near the surface back over to that side of the convection cell. And so the same thing would happen on this side of the globe, right? Kind of gets up to there, starts cooling off. And as it cools off and moves, it starts sinking because it becomes colder and more dense. So how about I'll write that? Colder, more dense. All righty. And so as that comes down and pushes the air down and warms up a little bit, it causes it to basically do this. All right. So we have colder, more dense air. And also I should say that this is sinking. All right. So basically we have sinking here. Right. We have rising right there. We have sinking. Oops, sorry. Whoops, I got it. I guess I can't write up there. Sorry. So we have sinking. Well, imagine there's a G right up there, right? We have sinking air there. We also have sinking air here. And now this is a big, huge deal. This kind of convection current going on, and I'm not drawing all the stuff down on the bottoms. This is enough to draw for right now in the southern hemisphere. But what's really amazing and really cool about this is kind of the basis for what causes air to start moving around. It's this differential in heat. And so whether it's the equator and like the latitude's up a little above 30 degrees or, up around by 60 degrees where the air is relatively warmer again and being forced up again, it's these heat and temperature differentials that cause air to move around the globe. And depending on where we are underneath that, that can play a huge difference. Now, remind you, what we're drawing here, this is a model that shows if the Earth wasn't spinning, right? If it wasn't rotating around, this is kind of what we would get. But unfortunately, or more complicated, I guess, is that the Earth is spinning, and we'll come back and tackle that in just a minute. But I have to show you a quick little demonstration first, and I think this one will work. So give me a quick second here, and you might laugh at my prop here, but it's the only plastic bottle that I have. It was an old plastic alcohol bottle that I would use for like marinating chicken and things like that. So oops, let me share my right screen. Oh, I need to put a little water in it. So give me 10 seconds. I'm going to fill this up with water, this bottle here of water, and then I need to show you a quick little experiment. So I'm going to stop sharing here, and we're going to see what happens within this. It's going to model the atmosphere. So give me 10 seconds. I'll be right back. All right, so I have a bottle. Now I need to find the cap. That's kind of the important part. Hold on, I think I might have left it out in the kitchen. I did. Thank you for putting up with my foibles and idiosyncrasies. I appreciate it. All right, so now here's the next thing I'm going to do. In this bottle, I'm going to take a piece of paper here, and I'm going to light it on fire, because what we're going to model is this is kind of like oceans down here. This is going to be our atmosphere. But it turns out in order for things to happen, for clouds to form, you need pollution in the atmosphere, microscopic particles of dust or microscopic, pollutants that come from cars, things like that. So what I'm going to do is I'm going to burn this. Smoke also is smoke particles are also a good particulate matter that rain can condense upon. They call that condensation nuclei. So check this out. I'm going to light this on fire. Maybe. Okay, so you can see. I'm going to put it in the bottle. So there's a little bit of smoke in there. Hopefully you can see that. Now I'm going to put the lid on. It should be pretty airtight. And I hope this model works here. But what I want to do now is I want to demonstrate what happens underneath different pressure regimes. So when you have air that's high pressure, what happens to clouds? And you're going to see in here. And what happens when air is under low pressure? What happens with clouds? So I'm going to squeeze this bottle a couple times back and forth. All right, so give it a second here. Okay, so when I squeeze, maybe you can see my eyeball a little bit better through there. And then when I let go, there's like a cloud formed. Oh, here, let me change the light. Maybe that'll help a little bit there. Let's see here. So, no, come on, light. So I'm going to squeeze, cloud goes away. I let go, cloud comes back. I squeeze, cloud pretty much goes away. Man, sorry, that's so doggone loud. This plastic is thicker. I'll try to get a better water bottle for next time. But my point here is that, well, let's see here. Maybe I wish I could get this stinking thing to work without a light. Let me see. Maybe that'll work. Where is this light coming from? Try this. Oh, what is this? I'm like, oh, it's from my monitor. Golly gosh. All right, so it's from my monitor that's doing all this. Maybe I need more light then to drown that out. Give me a second. Well, monitor is so bright. All right, so let's try this again. So I'm going to squeeze it and let go. So hopefully when I squeeze it, you can see my face and eye a little bit through there. And then when I let go, it becomes a lot less clear. So high pressure, when I squeeze it, basically the cloud kind of goes away. And when I let go and have low pressure, the clouds kind of come back. So that's the kind of the big point, and the whole thing I want to talk about there is when you have high pressure and you squeeze it, clouds go away. And when you have low pressure and let go, that's when the clouds start forming. And that's because it has to do with temperature. When you press and squeeze gases under high pressure, it causes temperatures to go up and it causes temperatures to rise. And that's not conducive to making clouds because it causes, basically it prevents the cooling of water droplets or water vapor. It prevents it from cooling down into water droplets. Whereas if you have lower pressure, like when I'm letting go, that change in pressure, that drop in pressure also causes a drop in temperature. And that's what allows the clouds to form. So going back to that drawing, I'm just going to come back and add to this drawing here. Maybe, you know, I got my cords all tangled up on it. And now I'm all out of breath. I don't know why. All right, so maybe it's just kind of too excited about this. Let me show you the next part. So I'm going to go back to my drawing here, or our drawing, and I want to show you a couple things. So let me see here. Yep. Okay, so back to our drawing. What's important about this? Well, where we have this rising air, what I'm going to draw, hopefully you guys will see this, is I'm going to draw, it's supposed to be clouds, all right? These are really bad clouds. It looks like a sheep or something. I don't really know what that is. But usually where you get lots of rising air, this is where you get big clouds. So I'm going to write right over here, rising air. And I'm going to also say low pressure. But here's the other thing, rising air, low pressure, that also generally equals clouds. All right, so rising air equals low pressure, which generally means clouds. So anywhere on the globe where we see rising air that creates kind of this differential low pressure, this is the big thing we should expect to see. So here's some rising air over here. Oops, rising air. So that is also going to be clouds, right? And then if you go up to about, so not only do clouds, I should mention this though, not only do we have clouds, clouds generally make precipitation. So that's the other big thing, right? There's a whole reason why we have all the rainforests and things like that in this part of near the equator, you know, just a little bit north and south of the equator. That's because that's where the rising air happens, and that's where the low pressure happens, and that's where temperature drops happen as that air rises and it starts cooling off. It cools off pretty quickly. It can make clouds, and that turns into the rain and the precipitation, which makes the equator so doggone wet, right? Kind of a really interesting thing there. Now, the same thing happens if you think about Seattle. Seattle is right up over in this area, like at 60 degrees north up here. Seattle is known for rainy conditions. And one of the reasons why it's known for that rainy conditions and stormy weather and things like that is, well, hey, look, it's right underneath kind of this global band of generally rising air and these low pressure systems and things like that. So up here, we'll draw a few more clouds. All right, we'll draw a few more clouds up over here, happy little clouds. Here's some clouds over here. So basically anywhere around this latitude, these latitudes up here where the air is rising, that's generally going to be where you would expect to find maybe cloudier conditions on a more regular basis. Same thing happening near the equator, and now, kind of down in this neck of the woods, down in the southern hemispheres, places like that. So that's low pressure. And this bottle really not really great. So I'll get another one to show you on Thursday here. But this would be like letting go of the bottle. This area down here, this rising low pressure would be like letting go of the bottle where the clouds disappear. The opposite of that then is if you squeeze the bottle or you squeeze the air, it causes the sinking air to basically heat up because it's being squeezed, it's being compressed. And so that's this part over here. When we have sinking air, right? So if we have sinking air, this creates high pressure. Oops, let me see here. So we have sinking air, we have high pressure here. And so if we have high pressure, it's just like me squeezing on that bottle, clouds disappear, right? So I'll just say no clouds. Maybe that'll be the easier, simpler way to saying it. So no clouds, and if there's no clouds, there's no rain. And so take a look where this is generally kind of falling down over the top of us. We are near that latitude. So basically everywhere you would see kind of in this part of the globe around this band is going to be a generally drier place compared to some of the other places in the world. So let me show you a really stark example of that really fast back on Google Earth. So let me go back and share my other screen here. Let me put this thing, ouch. Scraped my finger on my microphone, sorry. All right, so I'm gonna zoom out here and go away from our climatology there. But if you notice, right, you can already see a little bit of, hold on. You can already see how, right around this latitude, it seems like it's much drier. I'm gonna turn on the grid line so you can see where the equator is compared to everything else. But take a look at this, right? Near the equator or between the tropics of Cancer and things like that, this is where the rising air kind of ping pongs between, and we see a lot of green, right? It's a lot of green, and very similar things happen. Very similar things happen up in Canada and places like that. It's very green near these latitudes when you're away from the mountains. The mountains we'll see play a big role a little bit later on, but basically green, green, green. Now, if you follow those airs, the latitudes where we get a lot of sinking air, generally speaking, that generally happens right around this latitude in this part of the world. And you can see that sinking air is what helps lead to the big deserts that we have out there. And I mean, it's just this swath of dryness. And that generally corresponds. One of the big things that it helps correspond with is kind of that sinking air. Now, like I said, it's not perfect. It's not a perfect straight line. It's just a model. And our air is constantly moving and the streams of it are kind of shifting up and down, and it gets influenced by the continents and the shape of the continents. But this is a pretty good first step of thinking of how this air is moving around us. And you'll notice, right, also what's kind of interesting is by the Andes Mountains down here in Chile, it goes from really bright green and wet rainforesty areas to all of a sudden super dry, super deserty. I mean, there's mountains and stuff here, but it's super deserty on the other side. So I wonder what causes that. And that's kind of what we'll be looking at as well as we start moving forward here. All righty. So remember, all of this has been done so far with an Earth that hasn't been spinning around or hasn't been moving, right? So now let's see what happens if we start causing the Earth, taking into account the spin of the Earth. All right. So I'm going to show you this, and then we'll draw a few more things. And probably what that'll do is it'll get us to the end of today's class. And then when we come back, we have a bunch of breakout rooms for Thursday, where you guys are kind of applying all this stuff that we've been talking about. All right. So let's see what happens when we start spinning an object or spinning the Earth. And we're going to use a little model here on a merry-go-round. And YouTube has not been letting me publish some of the other classes that I use this video in, copyright claims or whatever, but I think it's okay if you put it on private settings. So check this out. All right, watch, have a look at this. Let's see what happens. Oops, let me share my video. Share my sound.
To show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Right, here's the game, right? You're going to throw the ball straight. So what's your name? Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
yeah,
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah. I don't know.
Right, what's going to happen, dude?
It's going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left, or by the person to the thrower's right?
Right.
All right, what do you guys think? So you don't have to tell me in the chat or anything. I just want you to make a mental guess here, right? Make a mental guess. Straight across, opposite, will be caught by the person that throws it. Will it be caught by the person on the left or to the right? So here we go.
The thrower's right.
Let's see what it is.
Right, in your own time, throw the ball.
I got this.
Gets better once you see the slow motion from the top.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea. It's called the Coriolis effect.
Coriolis.
It's very simple. It's objects
In
in
American
motion
English.
appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight. It's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis effect.
So basically, the Coriolis effect is this apparent movement and this apparent curving of, in this case, a ball, but it also affects the atmosphere in the air above us because the Earth, oops, let me see here. The Earth spins around, right? The Earth spins around its axis once every 24 hours, spins around like this. But if you're near the equator, right, it spins around the equator once in 24 hours And the diameter here around the equator, let me see what it is. Earth diameter, I can't remember, it's like 28,000, or not diameter, radius, circumference, that's what I'm trying to think. I can't spell. 24,901 miles, all right? So basically, this has to travel in 24 hours, 24,000 miles. That's how much the equator travels in one spin of the Earth, one revolution of the Earth. So that means if you're standing down at the equator, you are literally spinning at 1,000 miles an hour, a little bit more than 1,000 miles an hour, right? Kind of a weird thing to think about, but that's how fast it takes, because it's the Earth spins around once around its axis every 24 hours, and it has to do that in 24,000 miles in 24 hours. Now, if you go up near the poles here, right, the circumference of the Earth is much smaller, it's much shorter. And if I put it from the pole looking straight down, right, the equator's distance is this big circle. And you can see the higher up I go in latitude, the circles get smaller and smaller and smaller, which means the distance that it travels around is much smaller. So that means it doesn't travel as fast. It doesn't cover as much distance in the same amount of time as the equator. So it causes this relative difference in speed. I mean, the Earth is still one solid object being spun around like this, but down at the equator, it's a little faster, or a lot faster than at the poles. So how does that affect our atmosphere? Well, remember, our atmosphere is not stuck on the ground. It's not part of our mountains or anything like that. It's not like the ocean that is kind of stuck in between the ocean basins here. It's free to move. So how does that get affected when the Earth starts spinning? So let me show you here. This is a good way to explain it.
That formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same thing.
So I want to show you a couple of big things.
Imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling.
All right, so everything's traveling slower. I want you to look at this, what we call the apparent deflection, or the apparent way that this cloud moved. It wanted to go due north. So let me get me a little drawer thing here. Let me get my magic ink. Where's my magic ink? There we go. Let's see here. So it wanted to go due north like this. This is what it wanted to do. But because it had this faster speed to start out with, when it got into the slower things up here, it literally kind of jumped ahead and started going faster than everything, because it started out faster down here, which gave it this, what we call deflection, or this apparent deflection to what we would call the right. So in the northern hemisphere, it wanted to go this way, but it got deflected over this way to the right. And now I'm going to blow your mind. So watch this as they show it coming back down.
Slower,
right?
so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind.
So the other thing I want to show you here is, remember, I just showed you were moving to the right, trying to go up to the north like this, and we were trying to do that and then got deflected like this. Well, take a look at this cloud now. It started up here and it wanted to come this way. And if you were to put yourself in the shoes of this cloud right here, and you wanted to go straight ahead, and then you got deflected over this direction, that would be turning to your right. All right. So even though it looks like it's left on this picture, if you are in the footsteps of the cloud, or if you're a person walking this instead of a cloud, and you started here and you were walking forward this direction, but got deflected this way, that's a deflection to your right hand side. Okay. Same thing happens going this way. It wanted to go to the north, but got deflected to the right hand side. The exact opposite happens in the southern hemisphere. All right. So if it was in the southern hemisphere, down here is a cloud, it also wants to come this direction, or if it tries to come this way, it's also going to be much slower, and it's also going to fall behind, just like up here. But notice this, instead of going to the right in the southern hemisphere, it goes to the left. And the same thing happens if it were to try to go down like this and it was faster and gets sped up like this. Well, that's going to the cloud's left. So if you start out as a cloud up here, it gets deflected to the left in the southern hemisphere. So this is a big concept, and this is an important one because we're gonna end with
And the
this.
same thing.
I'm going to end with one last little drawing here, and we're going to add a few things to our little drawing, and then we'll call it good. And then we're going to then put you in breakout rooms next week to figure out what does it all mean and how does it work. And oh, yay, it's not broken right now, so that's great. Okay, so now we're going to add. Oh, doggone it! Let me get my mouse thing. All right, we are going to add, let's see here, what color should I make this? I'm gonna do green here. So, oh, maybe green, if I can choose the right color here. There we go. So I'm gonna call this the Coriolis deflections. And by the way, if we're launching rockets and things and stuff like that, the Coriolis effect on the Earth plays a big part, right? You can't aim from one spot to the next spot on the Earth and expect it to get hit in a straight line because the Earth rotates underneath it. That's kind of one of the big issues. So we're going to talk about this Coriolis deflections. We're going to draw this in green. And I just want to show you here, I'm going to draw a couple of things. If you take a look at our arrows over on the left-hand side, and our right-hand side, above the equator, we have arrows, this air that's wanting to come in like this, right? That wants to come in from the north to the south. So what I'm going to do is I'm going to draw what the air wants to do in these dotted lines, all right? So this is what the air wants to do in this band, in this region of the Earth. It wants to come down like this, I guess, would be the best way of saying that. All right, kind of like this, like that, piece of cake. So it wants to start out like that. Not a big deal. Ouch, my hand's hot because this thing's hits. But remember, in the northern hemisphere, so this is what I'm going to say, is I'm going to say, in the northern hemisphere, the deflection is always to the right. That's what I was just showing you a little bit earlier. The deflection is always to the right in the northern hemisphere. So in reality, instead of the air being able to go straight north to south, it gets deflected, right? It gets deflected just like this to the right, right? It gets deflected to the right. It gets deflected to the right, and it gets deflected to the right. So in the southern hemisphere then, remember in the southern hemisphere, everything gets deflected to the left, and it has to do with those differential speeds. So we have this air wanting to come in basically like this along the surface. That's what it wants to do. But in this case, it gets deflected to the left, to the left, to the left. So does that mean the southern hemisphere is like Beyonce's domain, right? Is it to the left or to the right? I can't remember that song. I think it's to the left. That's how you don't tell the joke, is you don't remember what the punchline is, but you get the idea. All right, so we get this big band of atmospheric flow down this way here, especially down at the equator, or just above the equator. If you get these flows wanting to travel from east to west, so we kind of get this big overall flow. Let me go like this, of the wind that wants to do this, right? Kind of a general overall flow of the wind that wants to do that. Now, let's just really quick here, I'll do the last little bit here before we go. If you go above that sinking air, right, at this latitude, the air wants to go up. If you're looking over here at these, you can see how the air is kind of going up, whoop, like this. And again, we're in the northern hemisphere, and so everything is deflected to the right. So it wants to go up that way, but then it gets deflected to the right. Gets deflected to the right. gets deflected to the right. And so because everything gets deflected to the right, we end up with this overall flow from west to east. And so we're going to have a name. We're going to put a name to these next week. But we get these cool spins and we get these cool things happening. And when you have opposing general flows of wind, it's kind of like a pitching machine. If you guys are into sports or anything like that, right? You have the two spinning wheels and the opposite spins, the opposite flows cause things to start spinning around. That's what's going to create weather systems spinning around. And that's what's going to bring atmospheric, moisture from one place to the next and things like that. So we're going to pause it right here. Next week, I'm going to give you, or not next week, but on Thursday, I'm going to give you lots of time to explore and take a look at this in real life and real action, and it won't just be a theoretical thing. And hopefully it'll be a little fun, and we'll go from there. So thanks for sticking through this. I'll get a better bottle that collapses and squishes easier and is better demonstration. And then we'll go from there. But that's all I got for today. So I'll see y'all on Thursday, and only three more classes left. So good job. You guys are hanging in there, hanging tough. So congratulate yourselves. I'll see you on Thursday. Alrighty.
Bye. Thank you. Have a good
Bye.
day.
Thank you.
Hi, I had a question.
Yeah, go for it.
So I'm not sure if you mentioned this before. I'm sorry if you already did.